Tonight, we're going to answer a question that sounds simple but gets darker the deeper you go. If we gave you the most advanced spacesuit humanity could possibly build right now, every material pushed to its absolute limit, every system engineered as far as current science allows, and then dropped you onto the surface of every planet in our solar system, how long would you actually last? Just you, your spacesuit, and whatever that world throws at you. Because here's the thing most people don't realize. The solar system doesn't want you there. Not on any of it. Every single planet, from the closest to the most distant, is actively trying to end you in ways that are stranger, faster, and more violent than anything you've imagined. By the end of tonight, you're going to understand exactly what our best technology would face on each of these worlds, and why Earth isn't just a nice place to live. It's the only place in the entire solar system where a human being doesn't need armor just to stay alive. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with what you already know. You are alive right now because of an extremely precise set of conditions. Your lungs are pulling in air at roughly 14.7 pounds per square inch. The temperature around you is somewhere within a range your cells can tolerate. Gravity is holding you to the ground at a force your skeleton was built to handle. The atmosphere above you is absorbing radiation that would otherwise shred your DNA strand by strand. You don't notice any of this. You never have to. Earth does all of it, automatically, invisibly, constantly. Now take all of that away and replace it with our best materials, all packed into a single suit. Layered titanium plating, a silicon carbide outer shell, an anti-corrosion coating built to resist acid, internal evaporative cooling loops, oxygen recyclers, multiple layers of radiation shielding. Every material advantage we currently have packed into one suit of armor. Now put that suit, and whoever's wearing it, on the surface of somewhere hostile. The pressure is wrong. The temperature is catastrophic. The air is poison. The sky itself wants to crush, boil, freeze, or dissolve everything inside that suit. That's what the rest of the solar system looks like. We're going to go through it, one world at a time. Let's start close to the Sun, with Mercury, the smallest planet, the fastest planet, and the first stop on this journey. Mercury has almost no atmosphere to speak of. What little gas surrounds it is so thin that scientists call it an exosphere rather than a true atmosphere. Surface pressure, there is less than 1/1,000,000th of what you're used to on Earth. That number alone tells you something important. There's essentially nothing standing between your suit and the vacuum of space when you're standing on Mercury. The good news is that a pressurized suit handles vacuum easily. That part of the problem is basically solved. The bad news is everything else. If you're on Mercury's day side, temperatures on the surface can reach 800 degrees Fahrenheit, or about 427 degrees Celsius. Your suit's evaporative cooling system starts working immediately. For the first several minutes, it holds the line. But without any atmosphere to scatter or filter it, direct sunlight hits the suit's outer shell with a violence Earth never lets you experience. Heat builds faster than the cooling loops can carry it away. At the same time, Mercury's magnetic field, while real, is extremely weak, only about 1% the strength of Earth's. There's no ozone layer either. That means the suit's radiation shielding is doing all the work alone against the full force of the solar wind. Within about 10 minutes, the radiation begins degrading the suit's internal electronics. Sensors start giving false readings. The cooling system's control circuits begin to stutter. By around 15 minutes, the combined heat load and radiation damage overwhelm the suit entirely. The cooling system fails. Internal temperature spikes. Whoever's inside is gone shortly after, somewhere around the 15 to 20 minute mark. That's the day side. The night side of Mercury tells a stranger story. Because the planet has no atmosphere to trap or move heat around, temperatures swing wildly between day and night. They drop to nearly -300 degrees Fahrenheit, or about -184 degrees Celsius, once the sun goes down. Here, the suit's thermal insulation actually has a fighting chance, since extreme cold is a problem engineers understand well. Radiation is still a constant threat, though, and over time, it still degrades the suit's systems. On the night side, a well-insulated suit could plausibly last closer to 30 minutes before radiation damage, and the sheer difficulty of shedding internal heat buildup catch up with it. Either way, there's no scenario on Mercury where even our best suit lasts an hour. What makes Mercury particularly unforgiving is the combination of threats hitting at once. Most planets present one or two major problems. Mercury throws vacuum, extreme radiation, and temperature extremes at your equipment simultaneously, with nothing in between to soften any of it. The planet's proximity to the Sun, on average about 36 million miles, means the sunlight striking its surface is roughly 7 times more intense than what reaches Earth. Add to that a rotation so slow that one Mercury day lasts about 176 Earth days. Some regions bake for months at a time. Others freeze in darkness for just as long. If there's anything close to a silver lining, it's that Mercury's permanently shadowed craters near its poles have been found by spacecraft to contain water ice. Cold, dark pockets on an otherwise scorched world. But that doesn't change what happens to even the best suit we can build, standing in direct sun on Mercury's surface. Mercury remains one of the fastest ways to lose a suit on this list. A place where even top-tier engineering is measured in minutes, not hours. Now move one planet closer to home, and somehow things get worse. Venus, Earth's so-called sister planet, similar in size, similar in mass, and yet almost nothing like Earth in any way that matters for survival. Venus has an atmosphere, and that's precisely the problem. It's 96% carbon dioxide. Surface pressure is about 92 times what you experience on Earth. That's roughly equivalent to the crushing pressure you'd feel nearly 3,000 feet under the ocean. Even a suit built with layered titanium and a reinforced silicon carbide shell is under immediate, constant strain the moment it touches down. Unlike a rigid, unmanned lander, a wearable suit needs joints. It needs flexible seals at the shoulders, elbows, knees, and waist, so a person inside can actually move. Those joints are the weak point. Rigid armor plating can be built thick enough to resist Venus's pressure for a while. Flexible seals cannot hold that line nearly as long. Then there's the heat. Venus's surface averages around 864 degrees Fahrenheit, or about 462 degrees Celsius. That's hot enough to melt lead. And that heat doesn't fluctuate much between day and night because the thick atmosphere traps and redistributes it so effectively. There's no cool side of Venus, no shadowed relief. The suit's evaporative cooling system starts working the instant you land, and it genuinely helps for a while. But the temperature differential between the outside of the suit and the inside is so extreme that heat keeps creeping in regardless. Within the first 10 minutes, the exterior panels begin to warp slightly under the combined assault of heat and pressure. The tantalum gold coating, designed to resist the sulfuric acid in the clouds, starts to degrade faster than expected, since acid exposure and extreme heat compound each other's damage. By around 15 minutes, core temperature inside the suit begins climbing, despite the cooling system running at maximum output. The joint seals, already stressed by the crushing pressure, start losing their integrity as the material becomes less flexible under the heat. Somewhere around the 18 to 20 minute mark, a seal fails, or the cooling system simply can't keep pace anymore, and the suit's structural integrity gives out. The supercritical atmosphere floods in almost instantly after that. Then there's the atmosphere's composition itself. High above the crushing surface, Venus's clouds are made largely of sulfuric acid droplets. Those droplets would have already been chipping away at any exposed seals or coatings during descent, before the suit even reached the ground. By the time you're standing on the surface, the acid has had a head start on weakening exactly the parts of the suit that need to hold the longest. It's worth noting that 30 miles up, conditions in Venus's upper atmosphere are far gentler, close to Earth-like pressure and temperature, which is actually why some scientists have proposed floating habitats in that specific layer. But standing on the actual surface strips away any of that theoretical relief. Soviet Venera landers, the only spacecraft to ever successfully transmit images from Venus's surface, offer a useful comparison here. They were rigid, unmanned titanium spheres, built with no joints, no seals, and no need to keep a human alive and mobile inside them. Even so, the longest one survived was 127 minutes, and most lasted far less. A suit built for a person to actually walk around in, with all those necessary points of flexibility, would likely fail well before that, somewhere around 20 minutes. Venus also rotates unbelievably slowly, and in the opposite direction from most planets. It takes 243 Earth days to complete a single rotation, which is longer than its entire year around the Sun. A day on Venus is longer than a year on Venus. None of that changes the suit's timeline much, since the heat and pressure stay constant regardless of where the Sun sits in the sky. It's just one more example of how strange and unforgiving this world is. There is essentially no scenario, no altitude near the ground, no shadowed valley, that offers relief on Venus. It stands as the single fastest way to lose even our best engineering anywhere in the solar system. Faster and more absolute than Mercury. Roughly 20 minutes. And for most of that final stretch, the suit is already failing faster than its systems can compensate. Mars comes next, and it's the planet most people assume would be the easiest of the bunch. They're right, at least compared to everywhere else on this list. Mars has an atmosphere, but it's thin, about 95% carbon dioxide. Surface pressure is less than 1% of Earth's. That's still low enough that a suit needs to stay pressurized the entire time, but it's a far gentler environment than Venus's crushing weight or Mercury's raw radiation exposure. A well-built suit handles Mars's thin atmosphere and low pressure without much strain at all. Temperature on Mars varies enormously depending on location, season, and time of day. At the equator during summer, it can occasionally reach a relatively mild 70 degrees Fahrenheit or about 21 degrees Celsius at midday. At night, or near the poles, temperatures regularly plunge to -100 degrees Fahrenheit or about -73 degrees Celsius or colder. That swing is significant, but it's well within the range modern thermal insulation is designed to manage. So, what actually limits how long you could stay? Two things, mostly. Radiation is one of them. Mars lost its global magnetic field billions of years ago, and without one, the surface has almost no protection from solar radiation and galactic cosmic rays. Data from NASA's Curiosity rover suggests that an astronaut spending extended time on the Martian surface would accumulate radiation exposure well beyond what's considered safe over the course of a normal mission. That's not a fast killer, though. It's a long-term, cumulative concern, something that matters over weeks and months, not minutes. The other limiting factor is dust. Mars experiences planet-wide dust storms that can last for weeks. The dust itself is fine, electrostatically charged, and it clings to everything, working its way into joints and seals over time. Given enough hours of exposure, it can start degrading a suit's mobility and its air filtration system. Put those factors together, and Mars becomes less about a sudden failure and more about a slow countdown. A suit built for Mars, unlike the 6 to 8 hour EVA suits used on the International Space Station, would carry a larger life support reserve from the start, since there's no quick trip back to an airlock a few hundred feet away if something runs low. Given that kind of extended oxygen supply and scrubber capacity, a single excursion on Mars's surface could realistically last somewhere around 10 hours before life support runs its course. Dramatically longer than anywhere else on this list so far. That's not because Mars is forgiving. It's because Mars is patient. The radiation keeps accumulating quietly in the background. The dust keeps working its way into every mechanism. The cold keeps pulling heat out of the suit hour after hour. None of it happens fast, but all of it happens constantly, and eventually something gives. It's also worth noting that Mars is the planet most actively being studied for eventual human missions, with multiple space agencies and private companies working toward crewed exploration in the coming decades. Every serious mission concept relies entirely on pressurized suits and habitats, precisely because the raw environment, however photogenic and inviting it looks in photographs, still offers no real margin for error without one. The thin red dust, the pink-tinted sky, the ancient dry riverbeds, all of it sits beneath conditions that even our best suit can only hold off for about 10 hours before something eventually fails. Jupiter changes the entire nature of this question, because Jupiter doesn't actually have a surface to stand on. It's a gas giant, built almost entirely from hydrogen and helium, with no solid ground anywhere beneath its swirling cloud tops. So the real question for Jupiter isn't how long the suit would last standing somewhere. It's how long it would last falling. At the cloud tops, temperatures hover around -162 degrees Fahrenheit, or about -108 degrees Celsius. That's a serious cold load, but well within the range a properly insulated suit is designed to handle, at least at first. Jupiter has essentially no breathable atmosphere anyway, since it's roughly 90% hydrogen and 10% helium, with almost no oxygen at all. That doesn't matter much to the suit itself, since it's carrying its own recycled oxygen supply regardless. The real problem starts almost immediately, and it's radiation. Jupiter's magnetic field is the strongest of any planet in the solar system, roughly 20,000 times stronger than Earth's. That field traps enormous radiation belts, intense enough that even hardened, specifically shielded spacecraft like Galileo and Juno have limited operational lifespans anywhere near them. Within the first minute of the fall, that radiation begins tearing into the suit's electronics. Sensors fail first. Then the cooling and life support control systems begin to glitch. At the same time, you're still falling, and Jupiter's gravity, about 2.5 times Earth's, means you're accelerating fast. Within the first 60 miles or so below the cloud tops, pressure climbs to hundreds of times what you'd feel at Earth's surface. No suit built from any known material can maintain its structural integrity against that kind of external force for long. Temperature climbs right alongside the pressure too, since deeper into Jupiter's atmosphere means closer to the planet's own internal heat. Jupiter actually radiates more heat than it receives from the Sun, a leftover signature of the energy released during its formation 4.5 billion years ago. Put the radiation damage, the crushing pressure, and the rising heat together, and the suit doesn't stand much of a chance. Realistically, the radiation compromises the suit's systems within the first minute or so. The combination of pressure and heat then finishes the job, crushing and deforming the suit's structure somewhere around the 2 to 3 minute mark, long before ever reaching anything resembling a solid layer. Because there isn't one in any meaningful sense. Deep enough into Jupiter, hydrogen gets squeezed under such extraordinary pressure that it transitions into a liquid. Deeper still, it becomes a strange state called metallic hydrogen, where hydrogen atoms are packed so tightly that electrons flow freely, giving that layer properties similar to a liquid metal. This metallic hydrogen layer is what generates Jupiter's monstrous magnetic field in the first place. Jupiter's most famous feature, the Great Red Spot, is a storm larger than Earth itself. Wind speeds there reach around 400 miles per hour, and it's been raging for at least 150 years, possibly much longer. If the fall happened to intersect with a storm system like that, violent turbulence would be added on top of everything else, though by that point, it would matter very little to the outcome. Jupiter has over 100 known moons, including the 4 large Galilean moons, discovered by Galileo Galilei in 1610. Io, Europa, Ganymede, and Callisto, each remarkably different from the others. Io is the most volcanically active body in the solar system, covered in active lava flows driven by intense tidal heating from Jupiter's gravity. Europa is thought to hide a liquid water ocean beneath its icy shell, one of the more promising places in the solar system to search for microbial life. And missions are currently in progress to study it more closely. None of that changes what happens to a suit falling into Jupiter itself. There's no ledge to land on, no solid ground to reach. Just an ever-thickening, ever more hostile atmosphere that gives even our best engineering, at the very most, 2 to 3 minutes before radiation, pressure, and heat end the encounter. The planet itself simply continues on, swallowing the moment entirely. Saturn presents almost the same fundamental problem as Jupiter, another gas giant with no true solid surface, but the details of falling through it tell a slightly different story. Saturn is famous for being the least dense planet in the solar system, so much so that if you had an ocean large enough to hold it, Saturn would actually float. That low density comes from its composition, roughly 96% hydrogen and a few percent helium, arranged in layers that get progressively denser and hotter the deeper you travel. At the visible cloud tops, temperatures sit around -285 degrees Fahrenheit, or about -176 degrees Celsius. That's considerably colder than Jupiter's cloud tops, since Saturn sits nearly twice as far from the Sun. A suit's thermal systems face a harder fight here from the very first moment. Saturn's gravity is close to Earth's own, actually, so the initial fall is a bit gentler than on Jupiter. That buys the suit a little extra time before pressure becomes the dominant threat. As the fall continues deeper, pressure climbs the same way it does on Jupiter. Saturn's larger overall size, relative to its mass, means you'd fall somewhat farther before pressure reaches truly crushing levels. Even so, within the first 100 miles or so beneath the cloud tops, both pressure and temperature climb well beyond anything the suit's structure can tolerate. Just like Jupiter, deep inside Saturn, hydrogen eventually becomes a liquid metallic layer under enormous pressure. That layer generates Saturn's own magnetic field, weaker than Jupiter's, but still many times stronger than Earth's, and still more than capable of damaging unshielded electronics over time. Realistically, a suit falling into Saturn holds together a bit longer than one falling into Jupiter, mostly thanks to the gentler gravity and weaker radiation. But the outcome converges to a similar place, somewhere around 4 to 5 minutes before the combined pressure and cold overwhelm the suit's structure and its thermal systems. What makes Saturn genuinely unique, of course, is what surrounds it rather than what's inside it. The rings. Made almost entirely of water ice, with a small amount of rocky debris mixed in, Saturn's rings span an enormous distance. They stretch out to about 175,000 miles from the planet, and yet in most places they're remarkably thin, often less than a mile thick. If the fall happened to pass through the rings before reaching the atmosphere, the suit would be moving through a field of ice, particles ranging from tiny grains of dust up to chunks the size of a house. Those particles orbit at velocities of many thousands of miles per hour relative to anything not moving with them. A collision with even a modest-sized ring particle at those speeds would tear straight through any suit ever built, well before the atmosphere itself became the primary threat. Saturn's moon system adds even more to the story. Titan, the largest of Saturn's moons, is genuinely one of the strangest and most fascinating places in the solar system. It has a thick atmosphere, thicker than Earth's in fact, composed mostly of nitrogen. It's the only other body in the solar system known to have stable liquid on its surface, though that liquid is methane and ethane rather than water, filling lakes and seas near its polar regions. Surface temperature on Titan sits around -290 degrees Fahrenheit, or about -179 degrees Celsius. That's brutally cold, but Titan's atmospheric pressure is actually close to Earth's, which means a suit here doesn't need to fight a crushing pressure differential the way it would diving into Saturn itself. That changes the calculation entirely. Instead of a suit failing within minutes, the limiting factor on Titan becomes how long the insulation and heating systems can keep pulling ahead of that relentless cold, which realistically could stretch to a couple of hours rather than a couple of minutes. In some strange sense, Titan might be the gentlest stop in the entire outer solar system for anyone wearing real protection. Then there's Enceladus, a small icy moon that captured global attention when NASA's Cassini spacecraft discovered plumes of water vapor and ice erupting from its south pole. That hints at a liquid ocean hidden beneath its icy crust, kept warm not by the sun, but by tidal forces from Saturn's gravity constantly flexing the moon's interior. Cassini spent 13 years orbiting Saturn, from 2004 until it deliberately plunged into the planet's atmosphere in 2017. In that time, it transformed our understanding of the entire system, revealing seasonal changes in Saturn's massive storms, the true complexity of the rings, and the surprising possibility of habitable environments on moons we once assumed were simple frozen rocks. None of those discoveries changed the basic outcome for a suit falling into Saturn itself. Extreme cold, crushing pressure at depth, and no solid ground to ever reach. A fall that ends the suit's usefulness somewhere around 4 to 5 minutes, while the rings and moons circling overhead continue their ancient orbits completely undisturbed by the encounter. Move outward again, past the orbit of Saturn, and you reach a planet that even most astronomers admit gets overlooked: Uranus. It was the first planet discovered using a telescope rather than the naked eye, found by William Herschel in 1781. It immediately expanded the known boundaries of the solar system. Uranus belongs to a different category than Jupiter and Saturn. It's classified as an ice giant rather than a gas giant, because beneath its outer layers of hydrogen and helium lies a thick mantle made of water, ammonia, and methane ices, all held under enormous pressure and heat, despite the word ice suggesting something cold and simple. At the visible cloud tops, temperatures on Uranus average around -357 degrees Fahrenheit, or about -216 degrees Celsius. That makes it the coldest planetary atmosphere in the entire solar system, colder even than Neptune, despite Neptune sitting farther from the Sun. It's a strange fact that scientists still don't fully understand, since Uranus appears to radiate almost no internal heat of its own, unlike every other giant planet. For a suit falling into that atmosphere, the cold is the first and most immediate crisis. The atmosphere itself is roughly 83% hydrogen, 15% helium, and about 2% methane, the methane being responsible for the planet's distinctive pale blue-green color, since it absorbs red light and reflects blue back out. There's no oxygen and nothing breathable, though again, that's a non-issue for a suit carrying its own supply. What matters is how fast that record-setting cold pulls heat out of the suit's insulation. Within the first minute, the thermal systems are already working at full capacity just to keep pace. As the fall continues, pressure begins building the same way it does on the gas giants. Though it takes longer here since Uranus's interior is less extreme overall than Jupiter's or Saturn's. Even so, the suit doesn't have long. Realistically, the combination of extreme cold and building pressure overwhelms even our best insulation and structural design, somewhere around 3 to 5 minutes into the fall. All before ever reaching any true solid layer, since, like the other giants, Uranus doesn't have a surface in any conventional sense. One of the strangest things about Uranus has nothing to do with its atmosphere at all. It's tipped over. Uranus rotates on its side, with an axial tilt of about 98 degrees, likely the result of a massive collision billions of years ago, early in the solar system's chaotic formation. This means Uranus's poles, rather than its equator, face the Sun for extended periods during its orbit. A single orbit around the Sun takes about 84 Earth years. Each pole experiences roughly 42 years of continuous sunlight, followed by 42 years of continuous darkness. If the fall happened during one of those multi-decade-long polar nights, it would be happening in complete darkness, despite the Sun technically still being up in the sky over other parts of the planet. Uranus has 13 known rings, much fainter and darker than Saturn's iconic bright ice rings, made largely of dark, carbon-rich material that reflects very little light. They went undiscovered until 1977, found through a technique where astronomers watched a distant star's light blink as the rings passed in front of it. The planet also has nearly 30 known moons, all named after characters from the works of William Shakespeare and Alexander Pope rather than mythological figures, a naming tradition that sets Uranus apart from every other planet. The 5 largest, Miranda, Ariel, Umbriel, Titania, and Oberon, are all icy worlds. Miranda, in particular, has some of the strangest and most chaotic-looking terrain ever photographed, with towering cliffs and jumbled, patchwork surface features that suggest a violent history, possibly involving the moon being shattered and reformed by past impacts. Uranus's magnetic field adds one more layer of strangeness to this already unusual planet. Rather than being roughly aligned with its rotational axis, the way Earth's, Jupiter's, and Saturn's magnetic fields are, Uranus's magnetic field is tilted about 60 degrees off from its rotational axis and is also offset from the planet's actual center. That creates an oddly lopsided and constantly wobbling magnetosphere as the planet rotates, something scientists still don't have a complete explanation for. Only one spacecraft has ever visited Uranus up close. Voyager 2 flew past in January of 1986, capturing the only detailed images and measurements we have of the planet to this day, nearly 4 decades ago. No dedicated mission has returned since, though planetary scientists have repeatedly named a Uranus orbiter as one of the highest priorities for future exploration, given how little we still understand about this world compared to its neighbors. For a suit falling into Uranus, none of that scientific mystery matters much in the moment. Extreme, record-setting cold from the first instant, building pressure as the fall continues, and an ending somewhere around 3 to 5 minutes. All of it happening within a planet that spends decades at a time with either continuous daylight or continuous darkness, tipped over on its side, quietly rolling around the Sun in a way no other planet does. Neptune sits at the very edge of the traditionally recognized planets, and it holds a distinction none of the others can claim. It's the only planet ever found through mathematics, before it was found through a telescope. In the 1840s, astronomers noticed that Uranus's orbit wasn't behaving exactly as predicted. It wobbled slightly, in ways that suggested the gravity of another, unseen planet was tugging on it. A French mathematician named Urbain Le Verrier calculated where that hypothetical planet should be. In 1846, an astronomer named Johann Galle pointed a telescope at that exact predicted location and found Neptune within about 1 degree of where the maths said it should be. It remains one of the great triumphs of predictive science in the history of astronomy. Neptune is another ice giant, similar in composition to Uranus, with a deep atmosphere of hydrogen, helium, and methane, surrounding a mantle of water, ammonia, and methane ices, all wrapped around a rocky core roughly the size of Earth. At the cloud tops, temperatures average around -353 degrees Fahrenheit, or about -214 degrees Celsius. That's nearly as cold as Uranus, despite Neptune sitting even farther from the Sun, about 2.8 billion miles away on average. Sunlight takes over 4 hours to reach it, compared to about 8 minutes for sunlight to reach Earth. Unlike Uranus, though, Neptune radiates a noticeable amount of internal heat, more than twice what it receives from the distant Sun. That extra internal energy helps power the most violent winds ever recorded on any planet in the solar system. Sustained speeds that have been measured at over 1,200 miles per hour, faster than the speed of sound on Earth. For a suit falling into Neptune, those winds are the immediate and dominant threat. No suit built from any current or near-future material is designed to withstand sustained supersonic wind shear. Within the first minute or so, the sheer mechanical force starts stressing joints, seals, and exterior plating well past their limits. Add in the extreme cold, working against the thermal systems at the same time, and the suit is fighting 2 catastrophic problems simultaneously from the moment it enters the atmosphere. Realistically, the wind shear alone is enough to compromise the suit's structural integrity within about a minute. Total failure follows shortly after, somewhere around the 2-minute mark, making Neptune the fastest way to lose even our best engineering anywhere in the outer solar system. When Voyager 2 flew past Neptune in August of 1989, the final planetary encounter of its historic mission, it photographed a massive dark storm system in the southern hemisphere that scientists named the Great Dark Spot. It was roughly the size of Earth, similar in concept to Jupiter's Great Red Spot, though it later vanished entirely, replaced by new dark storms that have appeared and disappeared in the years since. It's a reminder that Neptune's atmosphere remains dynamic and unpredictable, even from our distant observations. Deep within Neptune, under pressures that scientists estimate could reach millions of times Earth's atmospheric pressure, laboratory experiments and computer models suggest something genuinely strange might be happening. The methane in Neptune's interior potentially breaks apart under that pressure, with the carbon atoms compressing into actual diamonds that slowly sink toward the planet's core. An idea sometimes described as diamond rain. It hasn't been directly observed inside Neptune itself, but laboratory recreations of similar pressure and temperature conditions have produced exactly this effect, lending real scientific weight to the theory. Neptune has 16 known moons, and by far the largest and strangest is Triton. Triton is unusual because it orbits Neptune backward, in a retrograde orbit opposite to the direction Neptune itself rotates. That strongly suggests Triton wasn't formed alongside Neptune at all, but was instead a Kuiper belt object captured by Neptune's gravity long ago, similar in composition to Pluto. Voyager 2's images of Triton revealed active geysers, erupting nitrogen gas and dark dust particles miles into the thin atmosphere above its icy surface. That makes it one of only a handful of places in the solar system confirmed to have ongoing geological activity. That's despite Triton's surface temperature sitting at an almost unimaginable -391 degrees Fahrenheit, or about -235 degrees Celsius, among the coldest measured surfaces anywhere in the solar system. Because Triton's orbit is gradually decaying due to tidal forces, astronomers predict that tens of millions of years from now, it will eventually be torn apart by Neptune's gravity. That would likely form a spectacular new ring system, a slow-motion process already underway that won't reach its conclusion for a very long time. Neptune also has a faint ring system of its own, 5 main rings made of dust and ice particles discovered through the same star occultation technique used to find Uranus's rings. Neptune's rings are clumpier and less uniform, though, a structure astronomers still don't fully understand, possibly shaped by the gravitational influence of small nearby moons. No spacecraft has visited Neptune since that single Voyager 2 flyby in 1989. Everything we know about this distant blue world comes from one brief pass decades ago, combined with observations from Earth-based telescopes and the Hubble and James Webb Space Telescopes since then. That makes Neptune, along with Uranus, one of the least explored and least understood planets in the entire solar system, despite the wealth of strange, violent, and fascinating features hiding within its deep, frigid atmosphere. Beyond Neptune sits a world that spent most of the 20th century classified as the 9th planet before being reclassified in 2006. Pluto. Whether or not you consider it a planet, it's still worth including here, because it represents an entirely different category of environment from anything closer to the Sun. Pluto was discovered in 1930 by Clyde Tombaugh, a young astronomer working at Lowell Observatory in Arizona. After a painstaking search through thousands of photographic plates, looking for a faint, slowly moving point of light. It orbits the Sun at an average distance of about 3.7 billion miles. Sunlight reaching Pluto is roughly 1,000 times fainter than what reaches Earth. Dim enough that the Sun would appear as little more than an unusually bright star in Pluto's sky, rather than the recognizable disk we're used to. Pluto has a thin atmosphere, composed mostly of nitrogen, with small amounts of methane and carbon monoxide. Surface pressure there is roughly 100,000 times lower than Earth's, thinner even than Mars's atmosphere. For a suit, that near vacuum pressure is actually one of the easier problems on this entire list. Structurally, holding pressure against near vacuum is a solved engineering challenge. The real threat on Pluto is the cold. Surface temperatures there range from about -375 to -400 degrees Fahrenheit, or roughly -226 to -240 degrees Celsius. At that temperature, materials that are flexible and strong on Earth become brittle, almost glass-like. The suit's joint seals are the first thing at risk. Rubber and polymer components that flex easily at room temperature can crack under repeated movement once they're this cold. Metal components can suffer from a related problem, becoming more prone to fracture under stress. the suit's heating systems fight to keep critical components above their brittle threshold, and for a while, they succeed. But every movement, every flex of a joint, adds a small amount of mechanical stress to materials that are already operating far outside their comfort zone. Realistically, a well-insulated suit could hold out on Pluto's surface for perhaps 8 to 10 minutes before a seal or joint finally cracks under the combined stress of extreme cold and repeated motion. Once that happens, the near-vacuum atmosphere does the rest almost instantly. Pluto's surface itself is remarkably varied and interesting for such a small, distant world, something that surprised scientists when NASA's New Horizons spacecraft finally flew past in July of 2015, after a journey that took nearly 9.5 years to cross the solar system. New Horizons revealed a massive heart-shaped plain of nitrogen ice, informally named Tombaugh Regio after Pluto's discoverer. It also found towering mountains made of water ice rising up to 11,000 feet, evidence of possible ongoing geological activity, and a hazy, layered atmosphere extending far higher than scientists had expected. Pluto has 5 known moons, and its largest, Charon, is so massive relative to Pluto itself, about half its diameter, that the two bodies actually orbit a shared point of gravity located outside Pluto entirely. That technically makes them a kind of binary system rather than a simple planet and moon relationship. One full day on Pluto lasts about 6.4 Earth days. Because Pluto and Charon are tidally locked to each other, the same way our moon always shows Earth the same face, an observer standing on one specific side of Pluto would always see Charon hanging in exactly the same spot in the sky, never rising or setting. An observer on the opposite side would never see it at all. Pluto's orbit is also unusually elliptical and tilted compared to the other planets. For a portion of its 248-year orbit, it actually passes closer to the Sun than Neptune does, something that last happened between 1979 and 1999. Whatever category Pluto ultimately belongs in, dwarf planet or otherwise, the experience of standing on its surface in our best suit comes down to a slow, quiet countdown against brittle materials and relentless cold, roughly 8 to 10 minutes. Sunlight, there is so faint it would feel less like standing on a planet and more like standing on the edge of the solar system itself, looking back toward a distant, dim star that used to be your sun. Before we leave the inner solar system behind entirely, it's worth stepping onto the one other body most of us have actually seen up close, at least through the achievements of others. The Moon. Earth's only natural satellite, and the only other world human beings have physically walked on during the Apollo missions between 1969 and 1972. The Moon has essentially no atmosphere. Sometimes it's described as having an exosphere so thin it's barely distinguishable from a vacuum, with a surface pressure roughly 1/trillionth of Earth's. That puts it in a similar category to Mercury in terms of raw vacuum exposure. But here's what makes the Moon different from everywhere else on this list. This is the one world where we actually have real data, not extrapolation. Apollo-era suits handled the lunar vacuum and temperature swings for hours at a time, and modern Artemis program suits are being designed to do it even longer. Temperature on the Moon varies dramatically depending on whether you're standing in sunlight or shadow, since without an atmosphere to trap or redistribute heat, there's nothing smoothing out the extremes. During the lunar day, surface temperatures can reach around 250 degrees Fahrenheit or about 121 degrees Celsius. During the 2-week-long lunar night, temperatures plunge to around -208 degrees Fahrenheit or about -133 degrees Celsius. In permanently shadowed craters near the poles, which never receive direct sunlight, temperatures have been measured even colder. Among the coldest spots ever recorded anywhere in the solar system, colder even than the surface of Pluto. Those permanently shadowed polar craters are also where scientists have confirmed the presence of water ice. Future lunar missions, including NASA's Artemis program, hope to access that ice as a resource for drinking water, breathable oxygen, and even rocket fuel production, since water can be split into hydrogen and oxygen. Without a magnetic field of its own, the Moon offers no protection from solar radiation or cosmic rays. Astronauts on the surface, even inside their suits, absorb meaningfully higher radiation doses than they would on Earth, one of many long-term health considerations for any extended lunar stay. But compared to Mercury, the radiation here is far less intense, simply because the Moon sits so much farther from the Sun. The Moon's gravity is about 1/6 of Earth's, which is part of why Apollo astronauts appeared to bound and hop across the surface rather than walk normally. Put a suit like the one we've been imagining tonight on the Moon, and it holds up remarkably well. Vacuum is a manageable problem. The temperature extremes are severe, but survivable with good insulation. The radiation is a long-term concern rather than an immediate one. Realistically, a well-engineered suit could sustain a person on the lunar surface for many hours, possibly longer, limited mainly by consumables rather than any single catastrophic failure. The Moon is genuinely a fitting stop on this list, not because it's the most dangerous, but because it demonstrates something important. It's the one world in this entire journey where our best engineering doesn't just survive, it thrives. Since this list has been about the Sun's family, it feels incomplete not to at least glance directly at the star itself, even though obviously no suit could ever get anyone close to it the way we've been imagining for the planets. The Sun isn't a solid body at all. It's a massive ball of plasma, roughly 73% hydrogen and 25% helium, held together by its own gravity and powered by nuclear fusion happening deep in its core. There, hydrogen atoms are fused into helium under temperatures around 27 million degrees Fahrenheit, or about 15 million degrees Celsius, and pressures more than 100 billion times what you feel at Earth's surface. If our suit was somehow transported toward the Sun, the outcome wouldn't need a countdown measured in minutes or even seconds. It would be gone almost instantly, long before reaching anything resembling the Sun's visible surface. Even the Sun's outer atmosphere, the corona, reaches temperatures of over 1 million degrees Fahrenheit, or over 550,000 degrees Celsius, hotter even than the visible surface beneath it. A genuine mystery in solar physics that scientists are still working to fully explain. The visible surface itself, called the photosphere, sits at around 10,000 degrees Fahrenheit, or about 5,500 degrees Celsius, hot enough to vaporize any known material instantly. Beneath that lies the convective zone, then the radiative zone, then the core, each layer hotter and denser than the last. Energy generated in the core takes an estimated 100,000 years to slowly work its way outward to the surface through countless absorptions and re-emissions. From there, it takes just about 8 minutes to cross the 93 million miles of space to Earth once it finally escapes as light. The Sun contains about 99.8% of all the mass in the entire solar system, with every planet, moon, asteroid, and comet combined, making up the remaining sliver. Its gravity is what holds the entire solar system together, keeping Earth and every other planet locked in stable orbits that have persisted for roughly 4.5 billion years and will likely continue largely unchanged for billions more. The Sun constantly releases a stream of charged particles called the solar wind, flowing outward through the entire solar system at speeds that can exceed 1 million miles per hour. It's this solar wind, when it interacts with Earth's magnetic field near the poles, that produces the aurora, the northern and southern lights, one of the more beautiful reminders that our star is a constant, active presence rather than a fixed, unchanging light in the sky. Occasionally, the Sun releases much larger bursts of energy called solar flares and coronal mass ejections, sudden eruptions that can send billions of tons of charged particles hurtling through space. When a large one is aimed directly at Earth, it can disrupt satellites, power grids, and communication systems, a reminder that even from 93 million miles away, the Sun's activity has direct, tangible effects on modern life. The most powerful solar storm in recorded history, known as the Carrington Event, struck Earth in 1859. It caused telegraph systems across Europe and North America to spark, fail, and in some cases, continue operating even after being disconnected from their power sources, and aurora were reported as far south as the Caribbean. Scientists study events like that carefully, because a storm of similar or greater strength today, in a world dependent on satellites, GPS, and interconnected power grids, could cause disruption on a scale we haven't experienced in the modern technological era. The Sun is roughly 4.6 billion years old, and it's currently classified as a main sequence star. That means it's steadily fusing hydrogen into helium in a stable, predictable way, a phase of its life expected to continue for roughly another 5 billion years. Eventually, once the hydrogen fuel in its core runs low, the Sun will begin fusing helium instead, causing it to expand dramatically into a red giant. It will likely swallow Mercury and Venus, and possibly reach all the way to Earth's orbit. Though by that point, Earth's oceans will have long since boiled away and its atmosphere stripped, making the planet uninhabitable well before that final dramatic expansion ever occurs. After the red giant phase, the Sun will shed its outer layers entirely, leaving behind a small, dense core called a white dwarf, roughly the size of Earth, but containing much of the Sun's remaining mass, slowly cooling over trillions of years, far longer than the current age of the universe itself. None of that changes what would happen to even the best equipment we could build anywhere near the Sun today. It's simply immediate and complete destruction, with no meaningful timeline to describe, no minutes of struggle, just an instantaneous end, the moment anything crossed close enough to feel its true, unfiltered power directly. It's worth remembering, though, that the Sun is also the reason any of the survival stories on this list matter at all. The Sun's energy, filtered and moderated by Earth's atmosphere and magnetic field across 4.5 billion years, is what made life possible. That includes eventually curious, questioning creatures capable of building spacecraft and wondering about all of this in the first place, existing anywhere in this solar system to begin with. Between Mars and Jupiter lies a region most people picture as a chaotic field of tumbling boulders. But the reality is far emptier and far more interesting than that image suggests. The asteroid belt. Home to millions of rocky bodies, ranging from dust-sized grains to the largest object in the region, Ceres. Ceres is massive enough to be classified as a dwarf planet in its own right, roughly 590 miles across, making up about a third of the asteroid belt's entire mass by itself. For a suit standing on Ceres, conditions are broadly similar to Pluto or the Moon. There's an extremely thin exosphere, offering essentially no pressure to fight against. Surface temperatures averaging around -150 degrees Fahrenheit, or about -101 degrees Celsius, and no meaningful atmospheric protection from radiation. None of that is a fast killer for well-built equipment. The same brittle materials problem that limits time on Pluto applies here too, though Ceres' temperatures are noticeably milder, so a suit could reasonably expect to hold out for an hour or more before cold fatigue in the joints and seals becomes a real concern. What makes Ceres genuinely interesting, beyond survival statistics, is that NASA's Dawn spacecraft, which orbited Ceres from 2015 until 2018, discovered bright spots within a crater called Ocata. Those turned out to be deposits of sodium carbonate, salts left behind by briny water that had once seeped up from a subsurface layer. That hints that Ceres may still harbor a partially liquid reservoir beneath its icy, rocky crust, making it one of several unexpected candidates in the ongoing search for water and potentially habitable conditions within our own solar system. The rest of the asteroid belt is far less crowded than science fiction tends to portray it. Despite containing millions of individual objects, the region is so vast, spanning roughly the distance between Mars and Jupiter's orbits, that the average distance between asteroids is measured in millions of miles. Spacecraft have crossed the belt multiple times without any need for evasive maneuvers, since the odds of an accidental collision are almost vanishingly small. Most asteroids are remnants left over from the solar system's formation 4.5 billion years ago. Rocky and metallic material that never managed to coalesce into a full planet, largely because Jupiter's immense gravity kept disrupting and scattering anything trying to clump together in that region. A suit on a typical smaller asteroid would face a genuinely bizarre experience before any environmental threat even became relevant. Gravity on most asteroids is so weak, often just a tiny fraction of Earth's, that jumping too hard could theoretically launch a person into a slow, drifting escape from the object's surface entirely. In practice, the same manageable near-vacuum conditions that apply to Ceres, the Moon, and Pluto would still be the dominant environmental factor, giving even modest equipment a reasonably long window before anything critical failed. Having gone world by world, it's worth slowing down and looking closely at what actually happens to a suit's systems during those failure windows, because the engineering behind it is more specific and more consistent than most people realize. 3 things tend to break a suit: heat, pressure, and radiation, and they usually work together rather than in isolation. Heat is the most intuitive. Every material has a point where it stops behaving the way engineers expect. metals warp. Seals lose their flexibility or, in extreme cold, become brittle instead. Coatings degrade faster once heat and chemical exposure combine, which is exactly why Venus's acid clouds are so much more dangerous than acid exposure alone would be. A suit's cooling system can only move heat away so fast, and once the external temperature difference gets large enough, no amount of circulating coolant keeps pace. Pressure works differently depending on direction. On Venus, external pressure crushes inward, and the suit's joints, the flexible points that let a person actually move, are always the weakest link. Since rigid armor can be built thick, but flexible seals cannot. Deep inside Jupiter or Saturn, the same crushing logic applies, just delivered by atmosphere instead of a planetary surface. On worlds like Mercury, the Moon, or Pluto, it's the opposite problem. Near vacuum outside, pushing the suit's internal pressure to want to expand outward, which is a comparatively easier engineering challenge, since rigid pressurized shells handle that well. Radiation is the quiet threat that rarely gets top billing, but it's often the first thing to actually fail. Charged particles don't care about structural integrity. They pass straight through material and disrupt the delicate electronics, controlling life support, cooling, and sensors. That's why Mercury and Jupiter both lose their suits to electronics failure before heat or pressure ever finishes the job. So what happens if, despite all of that engineering, a suit actually breaches? The answer depends entirely on where it happens, but the physics is well understood. In near vacuum, the moment a seal fails, exposed moisture, saliva, the surface of the eyes, begins to vaporize almost instantly, a process called ebulism. Liquid boils when its vapor pressure exceeds the surrounding atmospheric pressure, and at sea level on Earth, that means water needs to reach around 212 degrees Fahrenheit or 100 degrees Celsius before it boils. Drop the surrounding pressure low enough, below what's known as the Armstrong limit, roughly 6.3% of Earth's sea level pressure, and water can boil at normal body temperature instead. That's around 98.6 degrees Fahrenheit, or 37 degrees Celsius, without any additional heat required at all. Every airless or near-airless world on this list sits well below that threshold. The popular idea of a body violently bursting apart in vacuum, often shown in movies, isn't quite accurate. Skin and blood vessel walls are strong enough to prevent immediate explosive rupture. The reality is closer to severe, painful swelling as tissues bloat with expanding gas. Unconsciousness, after a breach in near vacuum, arrives within about 10 to 15 seconds. That's not primarily from ebulism itself. It happens because blood carries oxygen to the brain based on partial pressure, and in near vacuum, oxygen simply can't remain dissolved in blood effectively. The brain is starved of oxygen almost immediately, regardless of how much oxygen the suit's own tanks might still technically contain. This is the same basic mechanism, though far more extreme, behind why pilots and astronauts train extensively for rapid decompression scenarios on Earth. On worlds where the failure mode is heat or crushing pressure instead, like Venus, the sequence is faster and more brutal. Severe thermal injury and structural collapse of the lungs and circulatory system happen almost immediately on contact, which is why a breach on Venus is measured in seconds rather than the minute or two a breach elsewhere might allow. The takeaway, across every world on this list, is the same. The suit isn't fighting one problem. It's fighting several at once: heat, pressure, cold, and radiation, all trying to find the weakest point first. And eventually, on every world we've visited, except Earth, one of them does. Putting it all together, a clear ranking starts to emerge, from fastest suit failure to longest. And it's worth walking through it as a complete picture now that every individual world has been covered. At the very bottom sits the Sun, though it doesn't really belong on a ranked timeline in the same way. Exposure there isn't measured in seconds, but in something closer to instantaneous destruction, a threshold so far beyond survivable that it exists in its own category entirely. Just above that sit the fastest planetary failures, Neptune and Jupiter, both around 2 to 3 minutes, driven by a brutal combination of violent winds or radiation, followed quickly by crushing pressure and extreme cold. Next come Uranus and Saturn, roughly 3 to 5 minutes each, where record-setting cold and building pressure overwhelm the suit's thermal and structural systems at a slightly slower pace. Then comes Pluto, at roughly 8 to 10 minutes, where the suit doesn't get crushed so much as it becomes brittle, its joints and seals cracking under the combined stress of extreme cold and repeated movement. Mercury follows at 15 to 20 minutes, a world where radiation and heat on the day side, or radiation and deep cold on the night side, slowly degrade the suit's electronics and cooling systems. Venus sits just above that, at roughly 20 minutes, the slowest of the truly hostile worlds to finish the job, but arguably the most punishing, since crushing pressure and extreme heat attack the suit's flexible joints from every direction at once. From there, the timeline stretches out considerably. Ceres offers something closer to an hour, thanks to milder cold than Pluto and very little pressure to fight against. Titan, oddly, might be the most forgiving hostile world of all, with its Earth-like atmospheric pressure removing the crushing threat entirely and leaving a well-insulated suit to manage extreme cold for a couple of hours instead. The Moon goes further still, offering many hours of real, tested endurance, since it's the one world on this list where actual spacesuit data exists rather than engineering extrapolation. And Mars, somewhat surprisingly, gives our best suit the longest working window of any hostile world covered tonight, roughly 10 hours. Limited not by a dramatic failure, but by the slow, patient accumulation of radiation, dust, and cold. And at the very top, holding a category entirely by itself, sits Earth, the only place on this list where survival isn't measured in minutes or hours at all. It's measured in the ordinary, almost unremarkable terms we live our whole lives inside without ever having to think about it. Terms like days, months, and years, without needing a suit at all. What's striking, looking at this ranking as a whole, isn't really the differences between these worlds. It's how quickly even our absolute best engineering runs out of answers. Strip away atmosphere, strip away magnetic field, strip away the very specific band of temperature and pressure that Earth happens to occupy. And even a suit built from every material advantage we currently understand buys minutes or hours, not a lifetime. That says something important about just how narrow the true habitable band actually is. Not just in terms of distance from a star, the traditional definition of a habitable zone, but in terms of atmospheric composition, pressure, magnetic protection, and temperature range all lining up simultaneously. A combination that, as far as we currently know, exists in exactly one place within the entire solar system. All of this raises an obvious question. If the environments are this hostile, how do astronauts survive at all, even briefly, when accidents actually happen? A properly functioning spacesuit solves most of these problems by recreating a small, personal version of Earth's atmosphere. It pressurizes the interior to somewhere around 30% of Earth's normal sea level pressure using pure oxygen, enough to prevent embolism entirely, while still providing breathable air. Insulated layers manage extreme temperature swings, and a reflective outer layer reduces radiant heat absorption from direct sunlight. Modern spacesuits, used on the International Space Station, and, during Artemis era, lunar missions are extraordinarily complex, sometimes described as miniature spacecraft in their own right. They contain life support systems, cooling loops filled with water to manage the astronaut's body heat during physical exertion, radio communications, and enough consumables, oxygen, water, and battery power, for a spacewalk lasting roughly 6 to 8 hours. Even with all of that protection, real-world incidents have shown just how thin the margin actually is. During a spacewalk in 2013, European astronaut Luca Parmitano experienced a water leak inside his helmet. It began filling his visor with liquid, gradually obscuring his vision and threatening to interfere with his breathing. That forced an emergency return to the airlock, guided largely by memory and touch rather than sight. A genuinely dangerous close call that led to significant redesigns of the suit's cooling system afterward. Going back further, in 1965, Soviet cosmonaut Alexei Leonov performed the first ever spacewalk. During his return to the capsule, his suit had inflated so much in the vacuum of space that he could no longer fit back through the airlock hatch. He was forced to dangerously vent air from his suit to reduce its size just enough to squeeze through. An early and largely improvised solution to a problem nobody had anticipated during a mission. Still, in the earliest days of human spaceflight. On Earth's own surface, the closest real-world analog to sudden severe decompression comes from rare, catastrophic aircraft incidents at high altitude. A sudden loss of cabin pressure can render passengers unconscious within roughly 15 to 20 seconds if oxygen masks aren't used quickly. That closely matches the same physiological timeline that applies the moment a suit breaches on so many of the worlds covered tonight. Since the underlying biology, oxygen deprivation at low pressure, is fundamentally the same phenomenon, whether it happens 40,000 feet above Earth or on the surface of the Moon. These real incidents matter because they aren't theoretical. They're documented reminders that the margin between a controlled, protected suit and a catastrophic failure can be measured in a matter of seconds. That's exactly why every layer of a spacesuit, every redundant seal, every backup oxygen supply exists specifically to buy time against exactly the kind of countdown we've been describing, world by world, throughout this entire exploration. None of this means these worlds are permanently off limits to humanity. It just means every single one of them requires technology, standing between the human body and the raw environment, and the specific technology needed changes dramatically, depending on which world you're talking about. For the Moon and Mars, the two most actively planned destinations for future human missions. The primary engineering challenges are pressurized habitats and radiation shielding, often achieved by piling several feet of local regolith over living quarters to block cosmic rays. Closed-loop life support systems capable of recycling air and water with extremely high efficiency. Matter too, since resupply missions from Earth are expensive, slow, and in the case of Mars, can take anywhere from 6 to 9 months one way. NASA's Artemis program aims to establish a sustained human presence on the Moon this decade, including a planned lunar base near the South Pole, specifically chosen for its access to those permanently shadowed craters containing water ice. That ice could be split into hydrogen and oxygen, providing both breathable air and rocket propellant without needing to ship every resource from Earth. For Mars, both NASA and private companies have proposed missions using a strategy called in situ resource utilization, essentially manufacturing what you need using local materials rather than transporting everything from Earth. That includes extracting water from subsurface ice deposits, along with a concept for eventually producing rocket fuel by combining Martian atmospheric carbon dioxide with hydrogen brought from Earth. The oxygen half of that equation has already been proven on Mars. Perseverance's MOXIE instrument successfully converted Martian carbon dioxide directly into breathable oxygen more than a dozen times before its mission ended in 2023, demonstrating the core chemistry that any future fuel or life support system would build on. For the gas and ice giants, meaningful human presence on or within the planets themselves remains firmly in the realm of speculative future engineering, since there's no surface to build on. Any human exploration would almost certainly focus instead on their moons, places like Europa, Titan, and Enceladus, where solid or semi-solid ground actually exists. Several of those moons even carry the tantalizing possibility of subsurface liquid water oceans that could potentially support microbial life, even if the surface conditions would still overwhelm even our best suit within minutes. This entire exercise, walking through every world and asking how long our best engineering would actually hold up, ultimately circles back to a much bigger question that scientists studying other star systems ask constantly. What exactly does a planet need to get right, simultaneously, in order to support life the way Earth does? Distance from its star matters, placing a planet within the so-called habitable zone, where temperatures allow liquid water to exist. But as this entire journey through our own solar system demonstrates clearly, distance alone isn't nearly enough. Mars sits within a reasonable distance from the Sun and still offers a thin, hostile atmosphere, while Venus sits closer still and represents the single most punishing surface environment covered tonight. Atmospheric composition and pressure matter enormously. A strong protective magnetic field matters enormously. Geological activity that helps regulate long-term climate matters too, and even the presence of a large stabilizing moon, as Earth has, likely plays a meaningful role in keeping a planet's axial tilt, and therefore its climate, relatively stable over hundreds of millions of years. Get any one of those factors significantly wrong, and you end up with something like what we've spent this entire exploration describing. A world that might look beautiful, might even look inviting from a distance. Orange dust, blue-green methane haze, swirling storm bands, and yet defeats even our best engineering somewhere between 2 minutes and a few hours before the environment ends the encounter completely. One factor we've mentioned only briefly deserves a closer look on its own, because it shapes the entire physical experience of standing or falling on each of these worlds, even before pressure and temperature take their toll. Gravity. Earth's gravity, by definition, is our baseline of 1g. Every other world on this list measures dramatically differently against it. On Mercury, gravity is about 38% of Earth's. A suit and its occupant would feel noticeably lighter there, roughly what a 160-pound person on Earth would feel like at about 60 pounds. Though in the short window before the heat and radiation finish the job, that lightness barely registers as anything more than a strange footnote. Venus, despite its similar size to Earth, has gravity at about 91% of Earth's, close enough that you'd barely notice a difference. Not that it matters much, given how quickly Venus's heat and pressure work against the suit regardless. Mars offers gravity at about 38% of Earth's as well, nearly identical to Mercury. That's part of why long-term human missions to Mars raise serious medical questions about bone density loss and muscle atrophy over extended stays. Since the human body evolved entirely under Earth's stronger gravitational pull. Studies of astronauts on the International Space Station who experience effectively zero gravity already show measurable bone density loss of about 1 to 2% per month. That raises real concerns about what partial gravity environments like Mars might do to the body across missions lasting years rather than months. Quite apart from anything the suit itself has to withstand. Jupiter's gravity, by contrast, is about 2.5 times Earth's, among the strongest in the solar system. A fall into its atmosphere accelerates considerably faster than a similar fall on Earth, compressing an already brief timeline even further as the suit descends into deeper, more hostile layers. Saturn, despite being the second largest planet, actually has gravity slightly stronger than Earth's, about 106%, a direct consequence of how much mass it packs in, despite its unusually low density. A fall into Saturn feels, at least initially, deceptively similar to falling on Earth, right up until pressure and cold make that similarity irrelevant. Uranus and Neptune both sit close to Earth's gravity as well, at about 89 and 114% respectively. The Moon, at about 17% of Earth's gravity, and Pluto, at a mere 6%, would both feel almost weightless by comparison, movement becoming slow, floating, and strange throughout an extended stay. Gravity doesn't change the fundamental engineering challenge of extreme pressure or extreme temperature, but it does shape the physical experience surrounding it. How quickly a fall accelerates, how a suit moves in low gravity, whether it feels anchored to a surface or drifting freely. Small details that add texture to an otherwise consistent and sobering set of outcomes across nearly every world we've covered tonight. Step back from the numbers for a moment and think about what these worlds would actually look and feel like during those windows of exposure, because the sensory experience varies just as dramatically as the physics behind it. On Mercury's day side, you'd be standing under a sky that's essentially black, since without an atmosphere to scatter light the way Earth's does, there's no blue sky at all. Just a harsh, blinding sun against total darkness, even at midday, with shadows cut so sharp and absolute they'd look almost painted onto the cratered grey ground. On Venus, you'd never see the sun directly at all.